Hello, welcome to my presentation. Today I'll be introducing a power-aware implementation of SLAM that uses customized, efficient, sparse algebra. My name is Bahar Asgari, a PhD candidate at the School of Electrical and Computer Engineering at Georgia Tech. My research interests in the field of computer architecture include but are not limited to domain-specific architectures for sparse matrix algebra. This work has been done in collaboration with my colleagues Ramyad Hadidi, Nima Shoghi, and my PhD advisor Dr. Hyesoon Kim. SLAM, or Simultaneous Localization and Mapping, is a key real-time task in almost all autonomous systems. Till now, several SLAM algorithms have been proposed, including direct, indirect feature-based, and semi-direct semi-dense methods. Besides, several studies have proposed various implementations on software and hardware, including architecture and microarchitecture for SLAM. Our work focuses on microarchitecture design of indirect feature-based methods such as EKF and ORB. Despite the advantages of the prior hardware implementations, they are not fast enough and power efficient to guarantee real timeliness under the limitations of power resources in autonomous systems. The reason is that they paid less attention to two aspects of SLAM that creates a performance bottleneck and increases power consumption. First, SLAM incurs many random accesses to the on-chip memory, and second, SLAM includes power-intensive matrix operations that reuse data frequently. Our observation is that SLAM consists of sparse computations that cause the first aspect and worsens the second one. In this work, we take advantage of the sparseness to jointly optimize latency and the power consumption of SLAM. In EKF and ORB SLAMs, the sparseness has the following structures which provides the opportunity for optimization. First, the sparse operation includes a sequence of matrix operations and sparse operands. Second, the sparse operand captures fixed size, small and dense blocks of data. And third, the correlated dense blocks are scattered over deterministic related locations. For instance, in EKF, a particular sparse operation accesses only the colored parts of an operand matrix shown in this slide. We take advantage of this structure in sparse matrices and propose Pisces to efficiently improve SLAM performance. The key insights of Pisces include the following. Pisces aligns the dense blocks of sparse data that are processed together and maps them to adjacent locations of the on-chip memory. Pisces implements a chain of sparse operations as a sequence of small dense operations. As a result, it accesses the on-chip memory only once to read a dense block and applies all required processes before writing it back. This way, it reduces the number of accesses to on-chip memory, a key factor that causes high power consumption. For instance, the figure in this slide shows an example of a matrix operation on two sparse matrices converted into two dense matrix operations. The building blocks of Pisces are 7 dense matrix operations, including matrix transpose, 4 matrix multiplications on various size operands, subtraction, and summation. The table in this slide lists the latency of each building block. The size of dense operands is defined based on the coordinate system. In our implementation, which is on an FPGA, on-chip memory indicates BRAM blocks. The microarchitecture of Pisces includes 2 levels of pipeline: an outer pipeline that streams chunks of data, that's the map in SLAM, into the FPGA, and an inner pipeline, the stages of which are the dense building blocks of Pisces. The number of stages of the inner pipeline and the combination of dense building blocks differs based on the algorithm. For instance, our implementation for EKF and ORB includes 6 and 4 stages respectively, as shown in the table at bottom. Besides the core insights, Pisces implements a few optimizations. For instance, we know that an agent is constantly observing new landmarks and stops observing some of the old ones. Therefore, we need to dynamically replace old landmarks with new ones. To use the memory space efficiently while these replacements occur, Pisces utilizes a simple compression scheme for mapping the landmark data to BRAM blocks as shown in the figure in this slide. We implement Pisces on a Zinc FPGA using Xilinx Vivado HLS. We use AXI stream interface and we set the clock frequency to 100 MHz. We compare Pisces against 3 recent hardware implementations for EKF and ORB slams. We also compare them with our implementation on a Raspberry Pi version 4 with an ARM processor. Our datasets for EKF includes a synthetic emulated environment, and for ORB we use the Euro-C dataset. First, we compare resource utilization and power consumption. As the numbers in this slide show, for EKF SLAM, Pisces employs fewer or an equal number of BRAM blocks while using up to 4 times more lookup tables and flip-flops compared to OneDSA and FSA. As this comparison suggests, Pisces trades BRAM for flip-flops and lookup tables to more efficiently consume the power budget. The impact of such a trade-off is about 3 times and 2 times less power consumption compared to DSA and FSA, respectively. Please see the paper for more details about these results and the breakdown of the power consumption. Power consumption, however, is not the only concern about the prior hardware accelerators. Therefore, here we first explore the latency of EKF SLAM. As the figure on the left shows, when less than 50 landmarks exist in an environment, regardless of the map size, OneDSA and FSA can meet the real-time constraints defined by a sensor with 60 or less FPS. However, as the figure on the right shows, as soon as the number of landmarks increases, none of the prior work are fast enough, even if the sensor rate is as low as 25 FPS. The speed up of Pisces stems from implementing the sparse operations as a chain of fixed-size dense matrix operations. We also compare the latency of 2 main steps of ORB SLAM. The prior work, ESLAM, focuses on accelerating only the feature extraction step of ORB, while our focus is on bundle adjustment. As the figure shows, although ESLAM extracts the features 8 times as fast as the implementation on ARM, it does not have a significant impact on total latency. On the other hand, Pisces significantly reduces the latency of local and global bundle adjustments. As a result, to meet real-time constraints, we can combine the two approaches if the available resources of the target FPGA allow. In this presentation, we focused on SLAM that plays a key role in the navigation of autonomous systems. However, with advancements in sensor technologies, SLAM performance is becoming a bottleneck for a faster and more accurate navigation. With a limited power budget in autonomous systems, performing the compute-intensive SLAM in real time is the key challenge. To solve this challenge, we proposed Pisces, a new approach to accelerate SLAM. To improve power consumption and latency, Pisces transforms the sparse matrix operation into a chain of fixed-size dense matrix operations, and It reduces the accesses to on-chip memory by enabling the data exchange between the functions. Thanks for watching this video. I would be glad to take questions in the live chat discussion.